When we hear the word electricity, we immediately picture a spark jumping from a doorknob, a flash of lightning, or a glowing bulb. It flashes, crackles, and glows, naturally attracting our attention. Compare that bright, crackling energy to pressing the accelerator in a modern electric vehicle. There is almost no waiting, and there is absolutely no mechanical roar from an engine struggling to reach its most powerful speed. If there are no explosions happening under the hood and no complex gears grinding together, what invisible force is actually pushing a 2-ton car down the road? As engineer Dr. Lev Nemotin explains, electricity acts as the showman supplying all the energy, but magnetism does the turning. To see how this works, imagine shrinking down to the size of an ant and climbing inside a rusting electric motor. To understand the forces that move our modern world, we have to look at the microscopic spaces where the real work happens. Here in the dark, an electric motor consists of 2 main parts, a heavy outer casing and a complex inner core wrapped in copper wire. The outside part remains still and is called the stator. The inside part rotates and is called the rotor. The stator stays while the rotor rotates. Around the stator are coils of copper wire. When electric current passes through them, it creates an invisible magnetic field. Engineers arrange the current so the magnetic field travels around the motor, like a stadium wave racing around a track. The inner rotor feels this wave and responds. It is pulled around the circle, constantly chasing the pattern, generating turning force called torque. This traveling wave eliminates the need for physical hooks or gears. Raw electricity is translated into motion across empty space. That empty space between the stator and the rotor requires our close attention. Every bit of magnetic interaction crosses this narrow ring of empty air, the air gap. The rotor must be close enough to the stator for the magnetic connection to remain strong, but wide enough that the 2 parts never touch. Maintaining this separation becomes difficult once the motor is running. The rotor spins thousands of times a minute, materials expand from heat, and the entire machine is shaken by bumps and sudden acceleration. If the gap is unnecessarily large, the magnetic coupling fails and wastes energy. If the gap is too small, the spinning rotor scrapes against the stator, damaging the machine. The ideal gap is a precisely calculated fraction of a millimeter, which is held steady despite thermal expansion and constant vibration. Stepping back out to the human scale, electric cars themselves are not a recent invention. People were driving them more than a century ago, which raises the question of why it took so long to create the fast, practical vehicles we drive today. A modern electric vehicle is less like a single invention and more like an orchestra of specialized systems working together. We rely on advanced batteries to store the energy, power electronics to control the flow, and software to coordinate the entire system. Among these famous advancements, the precision required to protect that air gap is rarely discussed. It is one reason modern motors can be compact, light, and powerful. When a car accelerates in near silence, it can feel almost supernatural, but it is simply nature's basic rules of electromagnetism, harnessed with remarkable skill. This hidden mover operates everywhere in our homes right now, sitting inside elevators, washing machines, and the simple fans that cool a room. Electricity attracts our attention because it flashes. Magnetism deserves our respect because it turns.